welcome to the second part of our training, the training being organized by Noble Mind team, titled Principles and Applications of Spectroscopy. And in this part, we shall be talking about nuclear magnetic resonance, which cover principle, proton NMR, carbon 13 NMR, and if time permits us, we shall be talking about elucidation of structures using NMR or joint elucidation, depending on the time available to carry out this task. My name is Samuel Adewale Adeboyega from the Department of Pure and Applied Chemistry, Laruke Akintola University of Technology, Ogbomoso. We all know that molecules consist of atoms. So in a particular molecule, the atoms, or each atom present, possesses nucleus. Okay, when these molecules are then placed, or you place a particular molecule in a magnetic field, the nucleus of some atoms in the molecule behaves like a tiny magnet. Okay, by the time you introduce a broad spectrum of radio frequency, you may call it radio frequency wave. Okay, when it's applied on the molecule, due to the presence of nucleus, okay, which were already behaving like a tiny magnet in the magnetic field, so introducing radio frequency, it allows the molecule to resonate in a frequency equal to the frequency being introduced. Okay, and resonance frequency of nuclei is then measured and is converted. It's been measured by NMR instrument, and is being converted to NMR spectrum, okay, which is displayed as it display all relevant frequency as what you can see as peaks. And we want to inform you that the height of each peak, okay, it represents amount of each nuclei. It represents amount of each nuclei that resonates at certain frequencies. Okay, the more the nuclei that resonates, the nuclei resonates, the higher the intensity of the peak. Okay, and the value of the frequency also gives information about the environment of neighboring atom. Okay, this previous illustration was experiment by Stangelak, which demonstrates that certain nuclei were referred to odd number nuclei possesses spin angular momentum. Okay, and he found out that orbital and spin angular momenta, they give rise to what is called magnetic moment. Okay, which means that they behave like a small magnet. Before they were put in extra magnetic field, you could see that the peaks has not been, the band has not been splitted. But in the presence of the extra magnetic field, which is north and south, you discover that the nucleus, okay, the atomic nucleus start to be moving about, and you call it spinning, and that made it to behave like a tiny magnet. So you could also see that before the field is applied, okay, and after the application of field, you see that there's a small difference in energy, and this is responsible for splitting of the energy. So an electron spin can only make two orientations, okay, that give rise to spin magnetic. You have positive or negative, plus half or minus half, and the consistent change in the orientation now in the presence of radio frequency waves, it gives rise to energy difference, okay. And you remember that in our previous studies we have earlier calculate the change in energy as Planck's constant multiplied by frequency, okay. In NMR spectroscopy, the nuclei flip between two energy levels as displayed by previous figure, and only atoms whose mass is odd number can absorb energy in the range of frequency that are analyzed. We are talking about radio frequency. So the size of the gap between the nuclear energy, which we may refer to as intensity of the peaks, would vary, okay, and that will strongly depends on the neighboring atoms in the molecule called molecular environment, okay. Change of magnetic field or change in magnetic field, not changing the radio frequency wave this time around, is what gives rise to nuclei in different molecular environments, okay. They flip at different field strength, and when you measure the field strength, you could do that by comparing it with the reference compound, which has a value of 0. And example of such reference compound is tetramethylsilane, TSM. Let's briefly discuss the reference compound. It has the formula SiCH3 into bracket 4. It is inert and it has ability to mix, okay, with several compounds. All hydrogen atoms in tetramethylsilane, they have the same molecular environment, so it enables them to give rise to a single peak, a sharp absorption peak, which is always higher than any other protons that you could find in other compounds, okay. Absorption of other atoms are now measured now and compared to reference compound, that is, their shift away from the reference compound on the spectrum, and the process is called chemical shift. You have that symbol and it's measured in parts per million. So let's talk about proton NMR. We display here the table showing the isotopes of hydrogen. We have proton, or you call it protium, deuterium, that is hydrogen 2, or tritium, hydrogen 3. And let's go to their natural abundance. You could see that the proton or hydrogen 1 covers about greater than 99.98% of all the isotopes of hydrogen. Okay, now when proton absorb energy, okay, you have proton in different molecules or different compounds like that. So the energy that's being absorbed by different hydrogen atom in a particular molecule or in the same molecule, the energy may differ. So because we have many protons in the same molecule, does not mean that they absorb the same energy. Okay, and the difference in energy will be defined by the type or nature of chemical environment or surrounding atoms which are around them. So let's look at these structures and see different types of chemical environment. You could see in the first one, you see carbon that's been bonded to 3 hydrogen atoms. Okay, the 3 hydrogen atoms are on the same carbon. Okay, and that carbon is being bonded to another carbon atom. Now, for you to determine the environment of protons on a particular carbon, you will be considering the neighboring carbon atom, the nature or type or number of protons that are present in the neighboring carbon atoms. Okay, so carbon that the one carrying 3 hydrogen is bonded to carry 2 hydrogen, which are directly attached to carbon, and the 3rd hydrogen is being attached to oxygen that is also attached to that carbon. So in this, the environment of the first carbon hydrogens is one environment. On the second carbon atom, 2 hydrogen that are attached directly to that second carbon, they carries one environment, and the one that is being attached to the oxygen is in another environment. It's attached to electronegative atom. So we have 3 chemical environment in short. So let's look at the second structures. The first carbon carries 3 hydrogen and is attached to another carbon which carries 2 hydrogens. Okay, and let's check the last carbon also. It's attached to it carries 3 hydrogens and is attached to another carbon which carries 2 hydrogens. And from that we could see that the first carbon and the last carbon atom, hydrogens on those 2 carbons represent single environment. Let's look at the 2 carbons at the middle, maybe by your left or your right. Each of them carry 2 hydrogen atoms, and let's pick carbon 2. Let's pick the second carbon. Okay, if you pick that, to the left of the carbon it's attached to another carbon carrying 3 hydrogen, and to the right it's attached to a carbon carrying 3 hydrogens. So if I'm checking carbon 3 as well, there is a similar environment to it. So the 2 of them are in this, the protons on the 2 of them are in the same environment, and generally we have 2 chemical environments or 2 different protons. let's check the structure 3. If you observe very well, check the carbons, the carbon that carries the hydrogen. You will take each carbon one after the other. Take each carbon, look at the carbon attached to it. Okay, how many hydrogen atoms does it carry? Take the other carbon, how many hydrogen atoms does it carry, and look at if each of the carbon, you pick carbon 1, is attached to another carbon which carries the same or similar number of hydrogen atoms and is similar to what you have in carbon 2, you group the hydrogen atoms to have the same environment. Okay, so you could make a trial and check that to understand more about what environment is. Proton with identical environment, like I've been explaining, are shown with the same colors, the same color. So number of signal, as you could see, the number of environments that you have will represent the number of signals that are expected on the spectrum. Don't forget, the number of environments that you have represent the number of signals that you are expecting on the spectrum. Let's talk about something very important as well: splitting and multiplicity. You may have a signal on the spectrum being divided or being split into different lines, which you call peaks. Okay, signal split into peaks, and you could refer to that as splitting or multiplicity. Okay, signal splitting is an important feature in understanding NMR spectroscopy, okay, in structural illustration. So generally we have a formula to represent the multiplicity of a proton signal, which is given by m equal to n plus 1, where n is the number of neighboring proton. So splitting is caused by hydrogen on the same you call it Gemini, on the same carbon atom, or you call it Gemini hydrogen, or on the neighboring carbon atoms, which you call vicinal hydrogens. And we say that only hydrogens that are non-equivalent, so if hydrogen are in the same environment, they cannot split their signals by themselves. So it is only hydrogens that are in another environment, okay, that could split the signal NMR proton signal. Signal could be split into doublet, triplet, quartet, and so on and so forth. You could have multiplet. Okay, let's look at this. In this structure you have 2 carbon atoms and one carrying environment of proton HE, labeled HE, and the other one proton labeled HB. You could see that HE has 2 hydrogen atoms, HB has only 1 proton, and other bonds which are not shown may imply that you have maybe a key group or something else. So let's look at HA. Okay, we pick HA, we actually have 2 hydrogen atoms. That's, we will still discuss about that. But okay, the 2 hydrogen atoms has 1 environment, which you are expecting 1 signal. Okay, in that 1 signal, we now consider what we call splitting. how many peaks would that one signal be split to? So that will make us to talk about the environment. And if you check the environment, the neighboring atom or proton to HA is HB, and HB is just one proton there. And don't forget, our multiplicity is n plus 1, so meaning that HB, the n in HB is just one proton plus 1, making 2. So for one proton you add 1 to it, and that means you are expecting 2 signals. Let's quickly compare the proton on the other carbon. The proton called HB is just one proton, okay, but the neighboring atom or the environment carries 2 protons. Neighboring carbon atom carries 2 protons. Okay, so it is these 2 protons that will split. I'm talking about HAs. It is the 2 protons labeled HA that will split the peak of HB, called splitting or multiplicity or what you call it. So, and we have 2 HAs, 2 plus 1 making 3. So that means you are expecting 3 peaks in the signal of HB. Okay, and if you have 3 peaks, we have given a term 2 plus 1, that 2 is our n, so it's called triplet. And you could see we give examples of compounds that could exhibit the protons that could have that kind of environment. Generally, to understand the nature of splitting of peaks, of signals into peaks, you have to consider what we call Pascal triangle. So if you are having 2 peaks, you have a particular signal being split into 2 peaks, you will be having 1 1, and the size will be the same. Okay, if you're having a signal which is being split by 2 protons when n equal to 2, that means you are expecting 3 signals at n equal to 2. Don't forget, multiplicity will be equal to n plus 1. So the nature of the peak you'll be having is 1 2 1, and that is obvious in triplets. You could see that in triplet, the middle peak is twice the other peaks, 1 2 1. So if your n equal to 3, you know the multiplicity will be n plus 1. So you have 1 3 3 1, and that is obvious in quartet. In quartet, you have the first proton and the second first peak. The second peak is 3 times the size of the first peak. The third peak carries the same, that is 1 3 3, and the fourth peak is also very smaller, 3 times smaller than the middle peaks. Okay, let's see some compounds here of a particular compound here and check what we are saying. Example is we have a compound with a molecular formula C4H8O. We just know the molecular formula, and we find out that we were informed that it has quartet, singlet, triplet, multiplicities. Okay, let's suggest how the structure could look like. Okay, singlet, triplet, and quartet. Okay, for you to have a quartet, that means that proton is being neighbored to 3 protons. Okay, 3 protons. And if you look at the structure, CH2 is bonded to CH3. Okay, that CH3 will be the one to split the signal of CH2, the 2 protons on the CH2. So, and what will you split it to? Multiplicity equal to 3 plus 1, which is 4. That is quoted. And we have CH3 being as a signal that will be split by the 2 protons on the CH2 as well. So we have M equal to 2 plus 1, which is equal to 3, that give you triplet. Let's find out where the singlet comes. If you look at CH3 that's been bonded to C double bond O and O, you could see that CH3 is just being bonded to a carbon carrying oxygen. So on that carbon, or that functional group carbon, there is nothing like protons. Okay, and once there is no proton on the neighboring atoms, that means there will be no splitting. There will be no splitting of signal. I'm referring to the one on C3 bonded to C double bond O. So that means N equal to 0. So, and the multiplicity now is now given to be equal to 1. So you are expecting a singlet signal, just one signal. Okay, let's move to what we call integral factor, or what some material call is integration. In NMR, integration give us information about number of protons or ratio of proton in a given signal, and that is done by measuring the area under each peak. So you seeing a signal being split into different multiplicity, don't forget that multiplicity will only tell you what type of environment that a particular signal is having, because it is the environment of that signal that will split the signal into peaks. So let's check. You have Cl, CH2, CH3, and we have found out that there are 2 environments here. You have environment A being split by environment B, and you have environment B being split by environment A. So environment A has 2 protons, okay, and is being split by 3 other protons, which is environment B. So 3 plus 1 is equal to 4. So you are expecting quartet. I'm talking about signal splitting now. And you have environment B being neighbor to 2 protons. So it's being split by 2 protons. 2 plus 1 will give you 3. So you have triplet. 1, 2, 1. So now this integral, or the area under the peak, is what tells us how many, the actual number of protons that are present. So you will measure, okay, you will measure the length or the size of that integral sign from where it starts to where it ends, and you will compare it with the integral sign of other signals. So if you check, look at the signal A having 4 peaks and signal B having 3 peaks. If you check the size of the integral sign, you could see that the integral sign of A could represent 2 when you measure, and the signal B represent 3. That means 2:3. Okay, that gives us the idea that there are 2 protons on the measurement where you have 2, and there are 3 protons on the measurement where you have 3. It's not always that it will measure 2 and 3. Sometimes you may have maybe 0.5 in length, 0.5 ratio 1.5, 0.5 ratio 1.5. If you divide them by common factors, you will see that 0.5 is 1 and 1.5 is 3. That means 1:3. That means where you measure the length 0.5 is equivalent to 1 proton, and where you measure the length of 1.5 is equivalent to 3 protons. That's how to go about it. Let's check the other spectrum. You could see you have 3 environments there. Okay, I mean 3 carbon atoms, which when you check it properly, it gives 2 environments, environment A and environment B. In that sense, environment A, okay, has 3 protons. Some will say, okay, there are 2 environment A, 3 plus 3 should be 6. No, it's not like that. We will use integral or integration to know the number of protons. So the height or the size of the peak, that okay, this one is taller than this or this one is smaller than this, cannot give you the information about number of protons. It only tells you the nature of environment. Look at environment A, which gives us a signal A. Okay, how many protons do you have? You have 6 protons. But how many peaks do you have? You have just 2 peaks. That means the neighboring protons to environment A is just carrying 1 proton, and 1 proton plus 1, that is multiplicity, will give you 2, doublet. That's the reason why you are having 2 peaks. So by the time you are checking the peaks or the different signals, forget about number of protons that could be there, but you could be able to know the number of neighboring protons by judging using the peaks splitting. But to know the number of proton, I repeat, to know the number of proton, you have to do that by measuring the area under the curve, which is called integral factor or integration. So if you measure the sign, check the signal B. If you measure that integral sign from where the curve started to where from where it curves in, I'm talking about when you have integral factor where it started, okay, to where it ended. If you measure the difference, measure that of signal B, compare it to that of signal A, you will discover that the signal A, the length is 6 times, okay, larger than signal B. That is 1:6. That means in signal A, where you have 2 peaks, there are 6 protons there. In signal B, where you have we call this multiplet, okay, because there are 6 protons that are splitting the signal B. 6 protons splitting signal B tells us that we have 6 plus 1, that is 7. You can see that those peaks there. So 1:6 tells us that okay, there is only 1 proton in signal B and there is 6 protons. There are 6 protons in signal A. Another important factor we talk about is coupling. Okay, coupling means interaction between 2 hydrogen nuclei. Okay, and okay, when you have 2 nuclei interacting, nearby nuclei interacting, and one is splitting the signal of the other into different peaks, okay, that kind of interaction could be termed as spin-spin coupling, or you just say coupling. Let's talk about that again. You have 1 proton on a particular carbon, you have proton on another carbon, and that means you have 2 environments. That means one environment will be splitting the signal of the other environment. Okay, that interaction, that is one environment splitting the signal of the other environment, the interaction is called coupling. So let's talk about coupling constant, J value or J constant. J value or J constant. Coupling constant, it measures the interaction between pair of protons, okay, that is spacing the peaks of protons which are coupled, and is given by this formula. J value is measured in hertz, and change in ppm multiplied by instrument frequency. And what is ppm? Is the spacing between the peaks. Okay, let's see this. If you have signal A and B, okay, and you have signal A having different peaks, okay, one peak at 6.2, 6.0, 5.8, 5.6. That means you are having a quartet here. Okay, the difference from one peak to another is what we measure. Okay, we measure it as 0.2. Don't forget, I'm not talking about the integral factor now. I'm talking about difference in from one peak to the other. You have 4 peaks in a particular signal. There will be a space between one peak to the other. Okay, that is measured to be 0.2. So if you have you measure the NMR spectrum of that peak using a machine with a 30 megahertz instrument, so you can calculate J constant or J value as that space change in ppm, 0.2 multiplied by 30 megahertz, which is 6 hertz. So if you have 2 environments with a coupling constant JAB, that means maybe A splitting B or B splitting A. Okay, that must be equal to, by the time you are checking the coupling constant for JBA, so you equate JAB to JBA. Let's look at the illustration. Okay, let's look at this signal. You have signal A and you have signal B. We have known that it is signal B that will split the signal of A. Number of protons in signal B will determine the number of peaks we will have in signal B. Okay, so you now have 4 peaks here on signal A, and you take the difference between the peaks, the ppm of the peaks, you discover is 0.2, and so it stated that the coupling constant of signal A, which is being splitted by signal B, if 2 protons are splitting themselves, the coupling constant with the one of B will always be equal to the one of A. Let's look at some few structures there. You have on this benzene ring, you have proton A on proton A and B on ortho position to themselves. If we are considering signal A, the HB is on ortho position. If we are considering HB, HA is also on ortho position. So the coupling constant value is always given to found between 6 to 9 hertz. And the one that are in meta position, you have J constant of between 1 to 3 hertz. If you have in para position, you have 0 to 1. Look at unsaturated carbon atoms, where you have two different environments. So the J constant is given like this, and so on, like that. Okay, you have trans and the one for cis. Okay, the trans protons and cis protons. So you see different coupling constant which was shown. Let's talk about different types of coupling. We may have geminal coupling, that is two atoms or functional groups bonded to the same carbon atom. You may be having different environment even on the same carbon atom, so it's called geminal or two bond coupling constant, which is given as 2J. Vicinal coupling, the hydrogen atoms are on adjacent carbon. You have vicinal or 3 bonds coupling constant. That means if you are an adjacent atom, in between the first carbon and the proton there's a bond, that is bond 1. The carbon atom that carries the proton is bonded to another carbon, that's bond 2. The carbon that the neighboring carbon also carry another proton, so that is bond 3. So before you get to, if you count up to 3 bonds before you get to the neighboring proton, it's called 3 bond coupling. But if it's only 2 bonds that you so there is also what we call complex splitting pattern. Okay, simple peaks, okay, such as you may have doublets or triplets, which also is splitting to another peaks. Okay, and that will be called you say doublet of doublet, doublet of triplet, and so on, like that. Let's talk about chemical shift. Okay, during when atoms, okay, when their nuclei are placed on when they are placed in extramagnetic field or applied field, okay, they spin. We have discussed that during our introductory part. So you have spin orientation up or down. Okay, you have spin state, but when they are placed in the radio frequency waves, you see them resonating in a frequency equal to the applied frequency, and you know that when a molecule absorbs photon of frequency, particular frequency, and it goes to excitation, it does relaxes. Okay, it does not remain in excitation. So each proton, when they relax, they release certain energy. This energy is converted to the ppm, which is known as a chemical shift. So energy released during relaxation of a resonating proton, which must have caused by absorption of frequency, okay, is relative, is compared to a standard in a magnetic field, okay, and is converted into part per million, and This is known as chemical shift. So to know a shift of a particular proton from the standard, you use tetramethicillin as a standard. So in proton NMR, and tetramethicillin has the protons on tetramethicillin has a chemical shift value of 0. So any values or any variation away from that reference is called chemical shift. There are different proton NMR chemical shift for the sake of structural elucidation. Protons that are bonded to okay, you have 3 protons, methyl group, if it's bonded to a methyl group, or alkyl group being bonded to 2 different carbon atoms. That's, you have a CH2 at the center. So if you check, the table of values is placed by the side. The protons which are on benzene ring, you see their shift away from the reference, and so on and so if you know, if you are given a chemical shift of particular proton, you could find out the type of proton, or the the type of proton, or where that proton is being attached. Okay, the type of compound the proton is being attached. So the table continues there, but let's talk about something: the factors affecting proton chemical shift. Affecting proton chemical shift. So we have electronegativity. If you have highly electronegative element which is being attached to a carbon that carries the proton, they are electron withdrawing group, so they will withdraw the electrons around the proton. So, and by the time you are removing the electron, it's termed deshielding. And if you have shielded the proton, that will result in chemical shift to the left. For you to know the left, you go back to the table, and it's called downfield. So when a proton is highly shielded, it results in decrease in chemical shift to the right, and that is called upfield. Okay, so it's being displayed by the figure that we have there. Another factor is anisotropy, and this is a property of a molecule where a part of the molecule opposes the applied field of the other. Applied field, and the other reinforces. So you have two influence. Okay, one part of the molecule reinforces the applied field, and you have the other part of the molecule opposing the applied field, and you could only find out in chemical, where chemical shift is dependent on orientation of neighboring bonds, and that is common in pi bonds. An example of such molecule where you have that is aromatic compounds, alkynes and alkenes. So, and it is useful characterizing the presence of aromatic or other conjugated structures. So, and another factor that could affect the chemical shift is hydrogen bonding. Presence of hydrogen bonding result in deshielding of protons, and thereby increasing the chemical shift. And you know that is related to electronegativity. You define hydrogen bonding as a bond between hydrogen atom and highly electronegative element. So let's talk about different types of solvent that are used in the NMR. We have deuterated water, deuterated chloroform, acetone. In short, solvent cannot be 100% deuterated. So it is believed that a deuterated solvent does not show a signal of its own, but it is not 100% possible to deuterate a solvent. So therefore you see a trace of solvent peak when you are observing a spectrum. So it is always good, the first thing you look for when you want to elucidate is to cancel the effect or the peaks due to solvent. So let's also see lastly the factors influencing the NMR spectrum. Presence of noise, and this noise is related to the impurity of compound. The another one is effect of temperature. You should try as much as possible to run your NMR the same sample at the same temperature, because if there is a temperature variation, it may affect the nature of signals that you observe. Ladies and gentlemen, on this part 2, this is where we shall stop, and in our next class we shall start from carbon 13 NMR. Thank you for listening.